chapter 14, which is kinetics. In chemistry, does anybody know what the field of kinetics deals with in chemistry?
So can we go back to that sheet just a second? I'll do my hardest to.
Well, it's going to be posted on Blackboard. So, you mean this thing right here?
Yeah, I mean, I'm trying to keep up with you in class. So.
Okay. Yeah, it's better to listen and pay attention, and then if you want to, I mean, you're just going to be writing something that's going to be posted on Blackboard. So if you need to go back and get it, then go ahead and do that. But, I mean, if it helps you to learn it by writing, go ahead, but try and keep up. So, all right. Anybody know what kinetics is? Yes.
Is it with the rate of change?
Something that, yes, in chemistry, what changes? What is the rate that we're looking at? So it is a rate. What's a rate of? Rate of reactions, chemical reactions.
Good work. Look at you knowing stuff.
All right, so we're going to be looking at something like A plus 2B goes to form C plus 3D. Right? That's a generic chemical reaction. If we have this reaction, probably made that one too big. So I'm going to have to make these smaller. We're going to look at the profile, the concentration profile of A, B, C, and D. All right, and this is going to be for time. We're looking at how the concentrations change with time. In chemistry, well, let's say in physics, when we talk about the rate of, for instance, if I throw a rock across the room, right, we could talk about meters per second or miles per hour. That's the rate of the velocity. For a velocity of a chemical reaction, what do you think the units are? Rate, the units for the rate. Is it going to be miles per hour? It's going to be concentration versus time, molarity per second. Right? The molarity is changing over time of the reactants and the products. What's happening to the molarities of the reactants? They're decreasing. What's happening to the molarity of the products?
Increasing.
They're increasing. So let's just take, if this is A, right, it's going to be, we're starting with exactly the stoichiometric amount of A and B, such that when the reaction's complete, both A and B are all gone. Right? So if this is my A, it doesn't really matter what this looks like, but we do know it's going down. Okay? Now, what is the stoichiometric amount of B that I've got? Twice that. Right? So I have to go up there, and so it's going to do that. Can you tell which one's going down faster, A or B? B is. Right? So the rate of B, how much B is changing, is faster than what A is. Right? By how much? Twice as much, because of the stoichiometry of that reaction. What's C going to look like? Okay, it's going to start and then go down more? Okay, it's going to go up. Such that if you added, if I didn't have to compress these to get it on the paper, if I added this plus this, anybody know what that would look like?
Zero.
It wouldn't be zero, but it would be a straight line across at whatever the initial concentration was. So this plus this will give you just a straight line. So the sum of the A reactant that's left plus the amount of C that's been produced is a constant. Right? However amount A is consumed, C is produced. All right, what will D look like? Will that look just like C? No.
3 times
Super
higher.
slope in the positive direction of B.
Yeah, and it's going to go up 3 to 3 times the initial concentration of A. Okay, so it is comparing how much this is going up to this one, how much faster is this one going than this one? 3 times. Okay. Now, we talk about the rate as being like the rate of A. If we have some value t starting at 0, right? Then the rate is going to be whatever the change in A is, right? That's the change in the A concentration. Divided by how long it took. So that's delta A over delta T. Now, that's the rate of A, right? What's the rate of B equal to? It's the same thing. Are they equal? 0 to T, going that distance from 0 to T. For the same delta T, right, is delta B over delta T equal to delta A over delta T? No. And what did we say that difference is? This one is related to this one by how much? Twice. It's twice. Okay, we do the rate of change in C is delta C over delta T, and this one is delta D over delta T. Now, how are these different? So here's my 0 to T. So here the change is this value right there. This is delta C from here to there is that delta C. Okay. So how is this delta C different than delta A there? Yes?
The delta C is under the curve while the delta T.
Yeah, but I mean, qualitatively,
They're the same?
they're not equal. Their sum would be a constant, but one is positive and one's negative. Okay, this one is a negative number, and this one is a positive number. Okay. Now, these are the changes. We want rate to be a number for a chemical reaction that is independent of whether we look at A, B, C, or D. Right? In other words, when we calculate the rate, if we look at A, we want to get the same value as C. How could we do that? If this is a negative number and this is positive, what would I have to do to one of these? I would have to put a negative sign in front of it. And that's what we do. Right? We're going to try and make this an equality. All of these being equal to each other. And so I need negative numbers in front of these. So that now these are positive numbers and these are positive numbers. Now, does this equal this? No. So what would I have to do in order to make these two things equal?
2.
Okay, I would either multiply this by 2 or divide this one by 2. So what we do is we divide it by 2. Right. Now, do those equal each other? Yes. Okay. And does this now equal these? Actually, it does. It does. Does this one equal these?
No.
Is there some way we can correct that?
Divided by 3.
Divided by 3. All right, so by defining rate in this way in terms of either the reactants or the products, then we can look at any of those and get the same answer by this relationship. Now, let's do this for the generic reaction. A plus B goes to form C plus D. All right, that's, here I put specific numbers 1, 2, 1, 3. If I had this, how would this rate work for this thing right here? Well, I would say it's equal to 1 minus 1 over A, the change in A over the change in the time, minus 1 over B, the change in the B concentration over the change in time, which is equal to 1 over C, the change in the C over the change in time, which is equal to 1 over D, the change in D versus over the time increment. Okay? Now, I think most of you have had enough calculus to say, all right, in the limit as delta t goes to 0, right? So I'm going to make this thing smaller and smaller until we've just got an incremental tiny delta t. What would the equation for the rate be? Maybe it would be 1 minus 1 over a dt, right, where that represents a derivative. You've talked about derivatives now in calculus, right? Most of you had a full semester at least of calculus. And I think you still talk about derivatives in the very first part of calculus. So what is this equal to? It's 1 over b db dt, which is equal to 1 over c dt, which is equal to 1 over d dt. All right, so in calculus, what does a slope represent? I mean, what does a derivative represent? It represents the slope. All right, so I gave away the answer. All right, so basically, if we want to find out what the rate of the of this reaction is right here, what does it represent on that plot right there? It represents the slope, right? This is the instantaneous rate. Instantaneous rate. And this represents an average rate. All right, so this equation is over some finite time period. And what happens to the rate of a chemical reaction as the reaction proceeds? It slows down. That is correct. Now, graphically, how do I see that the rate slows down? What's the rate here? It's the slope, negative of the slope here. And then the negative slope there. By the time it gets over here, it's the negative slope there. Is this bigger than that? The negative of that slope? Yes, it is. In fact, when you get to the reaction when it's done, what's the slope way out at time infinity? 0. So the reaction is stopped. And its maximum rate is right at the beginning. Right? So the more negative the slope of the reactants, the faster it's going, the higher its concentration. Right? So over, at any particular time here, the reaction rate is faster here than there. And the reaction here is faster than it is there. Yes?
How did you get the equation for average rate?
That's just the definition of, for instance, if you've got a car, right? And you're going on a distance, right? You measure the distance that you go, and then you divide it by the time, right? And that gives you your average rate of the speed that you did, right? Well, for a chemical reaction, concentration is what we're measuring instead of distance, but we're still doing it as a time period. So we measure the concentration at the start, and then we measure the concentration at the end, take that difference, and then divide by the time, and that gives us our rate of the chemical reaction, or average rate. Now, when you go somewhere, you're driving around, you drive, you go 30 miles per hour for a little bit, then you might hit the freeway and you go 75 miles per hour, then you hit some streets and you only go 10 or 15 miles per hour, right? Then some average rate is determined based on how long it took you to get that distance, so while you were changing your speed. That's the average, right? But that's not the same rate as when you were on the freeway. You were going, 65 miles per hour on the freeway. That's your instantaneous rate at any particular time along the way. You have an instantaneous rate, right? So that's the difference between this, right? When you take some long time period and measure what the average value is compared to what the instantaneous rate is at any particular point in the reaction. So in this case, if I measured the average rate between 0 and t, how would that compare to the instantaneous rate at t? Are they the same, or is one bigger than the other? The average is bigger because you're averaging over times at which the rate is bigger than what it is over here. At the end of this, that's the smallest rate along that whole time period. You've got a bigger rate, and it's getting slower as you go along, and so the instantaneous rate here is going to be less than what the average rate is between 0 and t. Okay. Any questions on that right there? All right. So I passed out. Very close. I passed out the worksheet, chapter 14 worksheet. All right. So the very first question on that chapter 14 worksheet looks like that. So, Mr. Pick, why don't you help me here, since it seems like you did need to listen to me as we were talking about this stuff. So, at a particular time in the reaction, the sulfur dioxide is changing at a rate of 0.4 moles per liter per second. At what rate is the oxygen changing? What is the rate of the chemical reaction? All right, so I'm trying to figure out how the oxygen is changing with time. Okay, so how did you get that? So here the SO2 is changing at 0.4, and so the oxygen is changing. Now, I will admit that is impressive. You got the right answer. So
it's a 2 to 3 ratio between the rate of change or the chemical reaction.
okay, so we've got the relationship that we were talking about is -1/3 the O2 dt is equal to 1/2 the SO2 dt, right? So you got a good feel for this without the having to do the equations, right? You see that's a 3 to 2, so it's got to be 1.5 times as great, and it's a reactant instead of a product, so it's negative. So that's very good. But if you didn't quite have that kind of feel, then you would say, all right, I need to figure out what that value is right there based on the way we've defined the rate right there. Right? So we define a rate this way. So you need to apply this general form right here to this specific chemical reaction. So specifically, I've got 1/3 minus 1/3 the O2 dt because it's a reactant, so I need the negative sign, and I need the 3 because it's got a 3 in front of the oxygen in the chemical reaction. And then over here, it's positive because that's a product, and I need the 2 because there's a 2 in front of the reaction. Okay, and what it's asking for, at what rate is the O2 changing? So that's asking, what is this value right there? How is the oxygen changing with time? So I can get this, and this is telling me what this is right there. Right? The sulfur dioxide is changing at 0.4 moles per liter per second. So if I know this is changing at 0.4 moles per liter per second, what does that have to be changing at? Well, I multiply by -3, and that becomes this. So I get -3/2 the SO2 dt is equal to what the O2 is changing by. Right? Algebra, if I multiply both sides by 3, that goes away. By -3, that goes away. And this becomes -3/2. Okay? So I know this is 0.4 molar per second, which then results in minus 0.6 molar per second. That's how much oxygen is changing instantaneously at this particular time when the sulfur dioxide is changing at 0.4 moles per liter per second. Questions about that? What is the rate What is the rate of the chemical reaction at this particular time? Is it 0.4 moles per liter per second? Is it minus 0.6 moles per liter per second? Or is it something different? Yes, Mr. Louie.
Is the rate 0.2?
Yes, it is. How'd you get that?
Because the original, well, I mean, for the SO2 was 0.4, so I just basically divided by 2.
All right, because the rate is equal to 1/2 the SO2 dt, by the way we define rate. So that's 1/2 times 0.4, or 0.2 molar per second. That is correct. We didn't have to do that one. We could have picked oxygen if we wanted to. And then what equation would I have? I would use rate is equal to minus 1/3 dO2 dt. What's the value for the derivative of oxygen with respect to time? What's the numerical value of that? Anybody? No, this is not equal to 0.2. That's minus 0.6. So when I multiply by minus 1/3, what do I get? Positive 0.2. So whether I look at the oxygen or I look at the sulfur dioxide, then I still get the same rate for that chemical reaction. If I looked at the rate of the carbon disulfide, what would I get for what is the rate of carbon disulfide? Minus 0.2, that is correct. Minus 0.2 moles per liter per second. And the carbon dioxide is positive 0.2 moles per liter per second. Okay. Now, I'll make sure we look at our learning objectives. Understand the concept of reaction rates. Use the coefficients of a balanced chemical reaction to express the rate of reaction in terms of the change in concentration of a reactant or product over time. All right, what do rates depend upon? All right, so we've now defined rate. Reaction rates depend on, I'm looking for 4 things, and we're going to discuss all 4 of these in this chapter. Yes, Mr.
Is
Louie.
it the coefficient? Like the
coefficient in the chemical reaction, that will, actually the stoichiometry doesn't really affect it, other than it might affect what the mechanism is, which then affects the rate law. So I mean, that's not what I'm looking at. In other words, the fact that there's a 2 there doesn't make a difference as into whether it's a 2 or a 1.
Temperature?
Yes. Temperature, yes. Temperature is one thing that will change a reaction rate. Things that occur at room temperature normally go slower than if you increase the temperature to 100 degrees. As you increase the temperature, the reaction rate will go up for most chemical reactions. And so we're going to talk about why that is. Yeah, Mr. Post?
Concentrations.
Concentrations, yes. Now that's kind of what, I think if you had gone a little further with that, then that might have been close to what the stoichiometry type thing is. But yeah, concentrations, or if it's gases, then pressures for a gas phase reaction, right? Because if you talk about a constant volume, what happens to the concentration if you increase the pressure of a gas? It goes up, right? So concentrations and pressures basically are the same thing when there's a gas involved, right? So if you increase the pressure, that will also increase the rate because it increases the concentration or how close the molecules are together, right? And how much more likely to collide when they're at high pressure than at low pressure. May know a third one?
Volume.
But that really affects the concentration. So, yeah, it's true that the volume will affect it, but it affects it because it changes the concentration.
pressure?
Yeah, and pressure really is the same thing. If you have a constant number of moles and and it's a gas, then you increase the volume, then it will decrease the pressure. All right, well, the other 2 are less obvious, I guess. Have you heard of a catalyst? Nice. if there's a presence of a catalyst. Or there are things called inhibitors. And we're going to talk about, at least we'll talk about a catalyst. Anybody know what a catalyst does? Yeah,
Yeah,
Mr.
it
Louis?
speeds up the rate of reaction.
It speeds up the rate of reaction, but how is that different than something that's in the reaction?
It doesn't affect the reaction.
Okay, it speeds up the reaction, but its concentration doesn't change. It's involved in the reaction, but it gets produced. It's involved in the reaction, but it doesn't get consumed. Its amount stays constant. So with a chemical reaction, the reactants go down in concentration, the products go up in concentration. A catalyst stays at the same concentration, or the same amount. All right, and hardly any group gets this one. It's because it's so vague. It's the nature of the reactants. That's a kind of a whole general thing. If you're familiar with sodium metal and iron metal, do they both react with water? Actually, they do. If you put, anybody familiar with seeing sodium, what happens when you put it in water? Yeah, it reacts explosively, very quickly, forms hydrogen gas, and you'll get actually, because the heat evolved, you can get the flame forming if you have a lot of sodium and you throw it into water. But does that same thing happen if you take an iron block and throw it in water? No. But if you come back in a month, you'll find that the iron has turned rusty reddish orange. Right? So that reaction does occur, but the sodium is much more reactive and occurs much faster than what iron, even though they're both metals. Right? So that's included in the nature of reactants. It's just the chemical reaction that you're looking at. And then something else is the state of subdivision. In other words, I now have a gas fireplace, but I used to burn wood in my fireplace. And in order to start that fire, what I'd do is I'd take some newspapers and I'd roll them up into a ball, stick them under the wood, and light the paper on fire. Whereas if I took the flat piece of newspaper and stuck it under the wood and tried to light the flat piece of newspaper, very ineffective, right? So by putting more surface area in contact with the flame, it then ignites much faster, right? And the balled up paper, all that surface is in contact with the oxygen that's required for the chemical reaction, and so it was much more effective. Right? Or if you take, a block of something, like anybody from like Iowa or the Midwest, grain silos, right? Periodically, now we take precautions. Periodically, silos, those things used to explode. Anybody know why that was? Because the grain that was in there would get very finely divided, and it became extremely explosive. If for some reason there was a spark, something rubbed against something and caused a spark, then it would explode. Right? But if you have just the grain, all in big pieces, then that's not flammable. Right? So when you take that and you form it like a flour, right? Then that will react much better because it's finely divided compared to like the wheat by itself, the kernels of wheat. Right? So that is something that does affect how fast something goes. Is increasing the surface area of a reactant oftentimes will cause the rate to go up. All right, we have something which are called rate laws. All right, where the first thing we're going to, of these four, the very first one we're going to do is the second one. Right? How concentration affects rates. Rate law has this form: x b to the y. Right. So this is concentration effects for A plus B goes to form C. CC plus DD. I guess I should put AA plus BB. In other words, if you have a generic chemical reaction, then the rate law will be dependent upon the product of the reactants raised to some coefficients x and y. Right, so x is the order of the A, of A. Y is the order of B, and N is the sum of x plus y, and that's called the order of the reaction. All right. K is called the rate constant. All right. So the rate, what are the units on rate of a chemical reaction? Mr. Louis?
Molars over seconds.
Moles per liter per second. Very good. Or molarity per second. Right. So the rate will be in moles per liter per second. When you have these concentrations raised to these powers, and in order to get those units, the units on a rate constant are molarity to the 1 minus n seconds to the minus 1, where n is what? N is the order of the reaction, and it's x plus y. Right. That way, that will give you units consistent with the rate. All right, the usefulness of a rate law is that if you know what the exponents x and y are, which 2 weeks from, let's say, I guess a week from next Wednesday, you're going to be doing a kinetics experiment where you'll be determining x and y for the reaction of di plus hypochlorite. Right, so experimentally, we'll determine how x do that. So you go into the lab, you determine what x and y are experimentally. Once you've determined that, and then, like you will do in lab, you'll determine what the rate constant is for the reaction. Once you have that information, then for any possible concentrations, you'll know what the rate is of the chemical reaction. That's the usefulness of a rate law, is it allows you to calculate what the rate is at any point in a chemical reaction once you've determined what x, y, and k are. Now, if this had been 3 reactants, are there chemical reactions that have 3 reactants? Yes. Do you know how the rate law would be different if this had been A plus B plus E? If there were a reactant E in there, how would the rate law be different? If there was a 3rd reactant, what would we do to make that rate law? We would just add another term right there. E to the E power, or E to the Z power. Right? The exponents here are not necessarily these coefficients in the balanced reaction. X does not necessarily equal A. Y does not necessarily equal B. Sometimes they do, and sometimes they don't. You have to experimentally determine it. Now, can X be any number? Like, what do you think X normally is? Do you think it can be like 20/19ths? No. It's normally a small whole number. So 1, 2, or 3, or a ratio of 2 small whole numbers. Right? So it can be 1/2, it can be 1/3, it can be 2/3, but it's not going to be something like 12/11ths. Right? It's either a whole number or a ratio of 2 whole numbers. Could it be the square root of 2? Do you think x could be the square root of 2? No, it can't be the square root of 2. You can't express that as a ratio of 2 whole numbers. Right? So it's got to be a rational number, not an irrational number like pi or square root of 2. All right, so you have your worksheet, and we will finish today by doing this second question, illustrating rate laws, and then we'll take the quiz. All right, so here we've got a chemical reaction of chlorine plus carbon monoxide goes to form carbonyl chloride. The reaction is 3/2 order with respect to chlorine, 1st order with respect to carbon monoxide, and 5/2 order overall. Do you see how you get 5/2 order from that? Right? First order means it's 1. 3/2 order, so you've got 3/2 plus 1 equals 5/2. The rate of a reaction is 2 moles per liter per second when the concentrations of both the reactants are equal to 1 molar. What will be the rate of the reaction when the chlorine is equal to 4 molar and the carbon monoxide is equal to 2 molar? All right, how would I write the rate law for this chemical reaction right here? Well, actually, we're given what the orders are, so what would I start with? The rate law is equal to K. Well, okay, so the reactant is chlorine. Okay, now is that to the X power?
5 halves, or 3 halves.
It's 3/2. We're told that the order is 3/2. So it's 3/2 for chlorine. And you can put a 1 there if you want, but normally when it's 1, we just leave it as that. So that's chlorine to the first power. I mean carbon monoxide to the first power. Right? So the statement of the problem gives us the rate law. We know under these conditions that the rate is equal to 2 moles per liter per second. How are we going to strategically determine what the rate is this way when we know the rate at one chemical concentration condition? We can solve for K. Once we have K, we'll be able to determine the rate at any particular concentrations. So K is equal to the rate divided by chlorine to the 3/2, carbon monoxide to the 1 power. So that's the rate is equal to 2 moles per liter per second divided by 1 mole per liter to the 3/2 and 1 mole per liter to the first power. All right, so anybody good at math, do that one in their head. 2 divided by 1 to the 3/2 and then 1. Yes, that's equal to 2. And what are the units on this? Molarity to the look at the notes, right? The rate constant units, molarity to the 1 minus n, seconds to the minus 1. So this one's going to be, what is it? What's the units on this molarity? To the first power, second power, 8th power, minus 12, minus 3/2. How did I get that? Molarity to the 1 minus n. What is n here? 3/2 plus 1 is 5/2. What's 1 minus 5/2? Minus 3/2. Are you awake? You can do that math, right? 1 minus 5/2 equals minus 3/2. Okay. So that's molarity. And what else has to be on here?
That's negative.
Seconds to the minus 1. Okay, so there's my rate constant. So now how do I get the rate when the concentrations are 4 and 2?
Just use the initial equation.
Yeah, I'd use K times the concentration of chlorine to the 3/2 carbon monoxide. So K is equal to 2 molar to the minus 3/2, second to the minus 1. Chlorine is 4 molar to the 3/2, and carbon monoxide is 2 molar to the first power. And if you plug that into your calculator, I think you get 32. And what are the units on that? You got molarity to the 5th power that you multiply 3/2 times the molarity of the minus 3/2, 1. So that's going to be moles per liter per second, which is what you better get with a rate.